Hey everyone. So today we're going to look at a probability model, a special probability model known as geometric probability models. So what is that? So a geometric model is the appropriate model to use for a random variable that counts the number of Bernoulli trials until the first success. Okay, so Bernoulli trials, as we know, have to have only two possible outcomes. That's success, that's P, and failure Q, which can be defined 1 minus P. So the probability of success, which is P, must be constant for each trial, must be the same for each trial, right? And then each trial has to be independent of the other trials. So let's take a look at some more with geometric models and the formulas. So geometric models are specified by one parameter, which is P, the probability of success. So since achieving the first success on trial number X requires us first experiencing X minus 1 failures, then the probabilities are really easily expressed by the formula that I'm about to give you. So here it is. It's P, and then we have it equal to Q, failure, the probability of failure, raised to the X minus 1 power, times P, the probability of success. So P is the probability of success, Q is the probability of failure, and again we can find Q by using 1 minus P. And X is just the number of trials until the first success occurs. All right, we can also find the expected value, which is the mean, mu, is equal to 1 over P. And then we can also find the standard deviation, which is sigma, and that's just found by taking the square root of Q divided by P squared. All right, so let's take a look at an example. So here's our first example. It says, suppose a computer chip manufacturer rejects 9% of the chips produced because they fail pre-sale testing. So let's complete parts A and B below. So part A states, what's the probability that the 8th chip you test is the first bad one you find? And then we'll do part B. That's what's the probability that the first bad chip you find is is within the first 13 you examine. All right, so first you have to determine whether the geometric model is an appropriate model to use. So we know that there are only two possible outcomes, defined as success and failure, because the chips are either going to pass or fail, right? Pass or fail pre-sale testing. So the probability of success is constant because the probability that the chip will fail pre-sale testing is 9%, and that's constant from trial to trial. The trials we see are independent because all chips are understood to be independent of each other. The outcome of one chip is considered random and doesn't affect the outcome of any of the other chips. So therefore, we can say yes, the geometric model is an appropriate model to use, and we'll use the formula that we just went over. So let's identify the probability of success here. It's 0.09, right, 9%. Probability of failure, which can just take 1 minus 0.09, and we'll get 0.91. And then our X, that X value, the number of trials until the first success occurs, this will be 8. So all we need to do is go ahead and crunch these numbers and plug them into our formula. So the formula will be Q 0.91 raised to the X minus 1, 8 minus 1 power, times P, which is 0.09. All right, so in this we can go ahead and use our trusty calculators, and we should get a probability of 0.047. All right, let's move on to part B. So we've already finished part A. Part B says, what's the probability that the first bad chip you find is within the first 13 that you examine? So for a discrete distribution, the probability over an interval is equal to the sum of each discrete probability in that interval. So the formula which will characterize the probability for this question will be this. Probability x is less than or equal to x is equal to the probability 1, the probability x equals 2 dot 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 plus the probability x equals 1 plus the probability of x. So we identify the probability that the first chip is a bad chip. So chip, and then you get 0, 0, 9, 0, right? Then identify that the second chip you examine is a bad chip. So you would have to do the probability x equals 2 equals 0.082. And we know how to calculate these probabilities already from previous understanding, right? So then we get these two, and then using the same process, identify the probability that each subsequent chip you examine is a bad chip. So you take the sum of the probabilities to find the probability that the first bad chip you find is within the first 13 you examine. All right, so again, find the probability that the first chip is a bad chip, the probability that the second chip is a bad chip, and then using this same process for these first two, identify the probability that each subsequent chip you examine is a bad chip. Take the sum of these probabilities to find the probability that the first bad chip you find is within the first 13 you examine. Once you finish the calculation, you should have a probability of 0.707. Just to make sure we're clear here, let's take a look at that first one. So to find that, you would be doing q to the x minus 1 power times p. Well, our q value is what we had from part A. We've identified that already, right? So that was 0.91. Our x is 1 minus the 1 in the formula times the p-value, which is the probability of success. We've identified that as 0.09. Okay, so 0.91 to the 1 minus 1, meaning to the 0 power, right? Anything to the 0 power gets us 1 times 0.09. So then we get 0.09 for that one. All right, and you would do the same thing for this one here. The only thing that changes is your x value changes to 2. And then again, you would do them all the way up through the 13th one and then sum them up.